taking a look at worksheet number 4 here, question number 3 here that we had for homework last night. It says 4-kilogram ball traveling north with this momentum. Usually we're given the velocity of it, right, rather than the momentum. That's not a big deal. Like, just because you see a little bit of a twist in a question, don't let it bother you, okay? We still treat questions that look almost the same. We typically treat them the same as other questions. So it has a momentum, collides with another ball traveling west with a certain momentum. 2 balls stick together and head off as one. What's the momentum of the combined masses? In other words, what's the final momentum? What's the final velocity? And then what's the initial momentum, the momentum before the collision? Now, there's a couple ways that you can tackle this. The first thing I'm going to do, regardless of how I decide to go about this, is to draw that diagram. This is a two-dimensional problem. Whenever we see, in this case, west and north in the same question, it's got to be x and y components. It's got to be. Funny angle, no funny angle, whatever. If you see north and west in the same problem, it's got to be a two-dimensional problem. So let's draw the picture here. We've got a 4-kilogram ball traveling north. Let's make that object number 1. Actually, let's bring it over here a little bit. And we have a momentum here of 11.2 kilograms meters per second. Usually we're given that velocity, but whatever, we'll deal with that later on. 2, object number 2 is moving to the west. So I'm going to make this object number 2 right here. Its mass is 6 kilograms, and its momentum is 18 kilograms meters per second. Now remember, this is our situational diagram. We're not worried about head to tail or anything like that. We're picturing ourselves in a helicopter looking down. This is what we'd see, right? From above, this is what we'd see. Now, where do you think that wreckage, for lack of a better term, is going to go after 1 and 2 collide and stick together? Ballpark. Don't give me an angle here, but ballpark. Yeah, it's going to go this way. We know because there's a momentum to the west, we're going to have a momentum to the west afterwards. If there's a momentum north before, we're going to have a momentum north after. So it looks like this is right, but some people this morning were getting really bothered by this, not so much in this question, but a couple other questions that we were doing. If you don't know where this is going to go, like, we're solving for this, right? We're trying to find this. If you don't know where it's going to go, that's okay. That's why we're solving for it, right? If you get this wrong and you guessed that it was going down like this, that's not a huge deal. It acts as a little bit of a detriment to us in terms of visualizing the question, but it's not going to lead us necessarily to a wrong answer. We need to get these black ones correct in order to get the answer correct. But if we guess where our answer is supposed to be incorrectly, then it doesn't really matter because we're going to solve for where our answer is going to be. Yep?
Do you ever have a question where it's our one card gets ahead of the other card and like...
All right. Now, some of you, all of you need to do X component and Y component. And we should write that down. And we should label this clearly, X component and Y component, so that we always know what we're doing. We always know which part of the question we're doing. It is so critical to distinguish between X and Y. So we should write it down so that we know it's X or it's Y. We're going to say PI is equal to PF for the X component. Now, usually what we do at this point is to say M1V1I plus M2V2I, right? Right? Can we do that? Absolutely. Absolutely we can do that. The only thing is we don't know what the velocity is, right? We're given momentum this time rather than velocity. So you can find velocity, right? We know that velocity is equal to momentum over the mass. So you could go back to object 1 and 2 and find the velocity of each one, right? How many people did that? Good. That's absolutely correct. Look at this. Look. I don't need to multiply M1V1I. I don't need to multiply M2V2I because I know what M2V2I is. M2V2I is 18. So why do I need to find the velocity by dividing by mass and then multiply by mass to get the momentum that I was given in the first place? You see what I'm saying there? So if you find velocity for each of those, whoops. If you find velocity for each of these, all right, that's fine. And go back and do it exactly the way that we usually do it. Or save yourself a little bit of work there and say, well, object number 1 has 0 momentum on the x-axis because it's all vertical, right? All y component. Object number 2 has a momentum of negative 18. When you find the velocity of object number 2, and then right here, multiplied it by mass, guess what you got? 18. Go figure. Now, we're going to solve for PF here for the x component, and it's just going to work out to be positive 18. And then we'll do the same thing for the y's. Again, distinguish it, clearly indicate that you're doing the y component. PI is equal to PF. Usually we'd say M1V1I plus M2V2I equals mass total times VF, but why don't we just say 11.2? Because mass 1 times V1, whatever that is, equals 11.2 on the y-axis, plus 0, because the second one's only on the x-axis, equals PF. Sorry, this should be negative 18, shouldn't it? PF here for the y component is going to be equal to positive 11.2 kilograms meters per second. Now do I have to convert that to velocity? You could by saying V is equal to P over M, or you could just say analyze the momentum. 18 this way, 11.2 this way. And then the resultant not the resultant velocity, but the resultant momentum would be the hypotenuse. Okay, how many of you did that? How many of you analyzed doing momentum like I did? Okay, good. And how many again did the velocities? Okay, good. I like this way a tiny bit better because I think it's a little less work, but not much, right? You did it the other way. If you're comfortable with that, then that's fine. P, by the way, works out to be, when you do the math here, 21.2 kilograms meters per second. And theta, always drawn from the start of your vector diagram, using the inverse tan function of 11 over 18 gives us 31.9 degrees north of west. Now, if you solved for velocity first, you would have gotten 2.12 at 31.9 degrees north of west. Go figure, the direction is the same. Direction of velocity is always the same as direction of momentum, right? You solve for velocity, some of you did at least, then you have to find momentum. I solve for momentum, now I have to find velocity. What I'm going to do to find velocity is simply say P is equal to M times V, or V is equal to P over M. The momentum is 21.2, the mass is 10, the velocity is 2.12 at same direction, 31.9 degrees north of west. Now, if you solve for velocity first, unlike me, then how are you going to get momentum? Sorry? Multiply by M, right? So I did V is equal to P over M to get velocity. You're going to have velocity. You're going to say P is equal to M times V to find momentum. Is that okay? I like the way I did it, but I'm biased. Really, objectively, I don't think one way is necessarily better than the other. I think it's just whatever your preference is for it. Now, you were asked one more thing, though. What's the momentum before the collision? How would we go about doing that? How do we go about finding the momentum before the collision, Jake? Okay, be careful. You have M1V1 and M2V2, right? 11.2 and 18. What you cannot do is say the total initial momentum is 29.2 because those are vectors on different axes, and you can't add a vector 11.2 to a vector 18 and get 29 unless they're in the same direction, right? So you can't just do that. Okay, remember that. Okay, remember that. On your unit test, you're going to come across something like that, okay? Do not just add vectors like that. Somebody had a hand up over here. Tana, was it you? Okay. It's not 29. Yep. Okay, there's two options here. Daniel, I'll check with you and see what you did in just a second, okay? You could say, okay, this is 11.2 initial, right? This is 18 initial. You could do the Pythagorean theorem, right? Daniel, is that what you did? You did something else? Don't tell me what you did yet, unless it's that. Was it that? No? Okay. This works. Absolutely. When you do that, you're going to get 21.2 at an angle of, well, the way that I drew it, I would get like 58 or whatever, because it's west of north, right? Daniel, what did you do?
Well, like I said, that the final momentum was 21.2, so that the initial momentum.
Exactly. Exactly. If you found the final, isn't it always the same as the initial? Right? Like, I don't need to do anything else. Any way you look at it, the momentum is not 29. Any way you look at it, the momentum is 21.2. Whether you calculate the initial momentum or you calculate the final momentum, it doesn't matter. There's a question, like I said, on your unit test, that's going to be something like that. Some of you are just going to add those together, just like that. Okay, and that's going to be wrong. If it's multiple choice, that option will be there. Remember to do it either find the final momentum like we did here and say initial momentum is the same, or find the initial momentum and final momentum is the same. Got it? There's another one that's like that you're going to see before the test. And I can't remember if it's on a practice course set or a unit assignment or what it is. Can't remember where it is. Maybe it's a quiz, I'm not sure. But you're going to see that. And I think it's a quiz, actually. And you see that quiz, inevitably the question I get when I give that question is, it asks for the question says, what's the initial momentum of the system? And the question that I get is, people say, like, do you mean final momentum? And my answer is, no, we mean initial momentum. But what's the difference? Nothing, really, right? The question asks for initial momentum. But if you're more comfortable solving for the final momentum, then solve for the final momentum, because it's the same as the initial momentum every time. Let's take a look now at question number 4 as an example. We did an example like this yesterday, an explosion type question with a funny angle. This will kind of serve as our second example, number 4. It says, a 400 kilogram bomb is at rest on a table and explodes into 3 pieces. 150 kilogram piece moves to the east, 100 kilogram piece moves south of west. What's the velocity of the third piece? Velocity is a vector, right? So it includes direction. We need an angle with this as well. First thing that we probably notice here is that we have a south of west and we have an east. East and west wouldn't tell me this, but south and west do tell me that I need to do X and Y components. And whenever I do X and Y components, I should draw a picture first. The picture is just, it's not a free body diagram. It's not a vector diagram. It's a situational diagram that basically allows me in a graphical way to write down my givens. Okay? You're in a helicopter. You're looking at it from above. This is what you want to draw, your situational diagram. So here's my explosion point in my helicopter. It's on a table, so a helicopter might not be Might not work here unless the table's outside. But see, yeah, you're hanging from the ceiling fan. Have you done that? You're looking at it from above. So it explodes into three pieces. One piece goes east. Draw it, east. Piece number one. It's a mass of 150 kilograms, and it's got a velocity of 150 meters per second. There's another piece, south of west. This is south of west. Its mass is 100 kilograms, and its velocity is 200 meters per second. And its angle is 30 degrees. Right, that's south of west, right? The angle is measured from the west, south from the west, or south of west. Now the third piece, I'm going to guess the third piece is going to go up here. I don't really know that for sure. Could go up here. It's going to go up, but we don't really know which way. That's okay. Remember we said a little while ago that red one, that final one that you're trying to solve for, if you guess wrong, that's not a big deal.
I don't understand
Yeah.
how you're even coming to the guess, but it's
Okay.
I'm gonna go with that.
Okay. So no, I'm glad you asked that question. So how do we come to the guess? It's an educated guess, but it still is a little bit of a guess that it's going up and left. Well, I'll be honest with you. The fact that I've got it going to the left is a complete guess. Like it's 50-50. I'm picking away. My gut is that it's going to go to the left, but it's 50-50. But how do I know that it's going up? I do know that it's going to go up. How do I know that?
It's because you need an equal and opposite force on all sides. So if you go to
Equal and opposite force and equal and opposite impulse, and therefore momentum.
technically, I guess, if
Yep.
and so if you're going,
What's the next thing you notice here? By the way, what's the mass of this third piece? We know this, right? We got 400 kilogram bomb that's exploding. 150 goes one way, 100 goes another way. It's going to be 150, right? So I'm going to write that down 150. I have no idea what the velocity of that is. I'm guessing the direction is the way that I have it drawn here. Don't really know. We're going to find that in a moment here. What's the next thing you notice that you got to deal with? You got a funny angle. And when you see a funny angle, you should think 5 words right away. I don't like funny angles. So let's take our funny angle off to the side and get rid of it. We've got 200 meters per second right here. And my angle is 30 degrees. I'm going to replace it with an x component right here. And I'm going to replace it with a y component right here. Now, mathematically, you can do this whether you've taken English math or French math. But if you're in the English class, you've spent more time on sine, cosine, tan than if you're in the French class. If you're in the French class, you can still do it. Okay? You've learned about sine, cosine, tan. You just haven't spent as much time on it. But you can also do it using the sine law. We're going to always use sine, cosine, tan because I think that's the way that leads to the best understanding here. But you do it whatever way makes the most sense to you. I'm going to say for x, which side of the triangle is that? Adjacent, hypotenuse. I'm going to use the cosine function, adjacent and hypotenuse. Cosine theta is equal to x over, or adjacent over hypotenuse. The adjacent side equals 200 cos 30, which I think is 173.025? 205? And the y component, well, that's just going to be sine 30 degrees is equal to opposite over hypotenuse. And that's going to be just 100 meters per second. I boxed this off, not because I have to, but just because I want to make this, I want to separate that from the rest of the question. It's the rest of the question that's the same as every other question. Right? The rest of it doesn't really change conceptually from one question to another. This is different. If I have a funny angle, this is different. Yeah? Yeah, I'm going to leave them as positive right here, although if you want to make them negative, you can do that. But in the end, when I sub them into my Pi equals PF, yes, they are both going to become negative. This one negative because it's left, this one negative because it's south. Okay, let's do the x component here now. Again, clearly identify that it's x. Do them separately from one another and clearly identify. Show that work. We say pi is equal to pf. We say 0 initial momentum because this bomb on the table is at rest. If it wasn't at rest, if it was moving, we just say m total times vi, right? But it's not moving. We don't have to worry about that. m1 v1f plus m2 v2f plus m3 v3f. Can we cancel out a mass? No, it's not the same, right? Notice number 5, though, which is the first one you're going to work on yourself. Bomb sitting at rest on a table explodes into 4 pieces of, you don't even know what the mass is. Doesn't matter, right? It's going to cancel. But in our example, it doesn't. M1 is 150. V1F is 150. M2 is 100. Oh, by the way, I think we talked about this in the example yesterday. If we want to, because remember that 200 meters per second is dead to us now. We're never going to use that again. That 200 is gone forever in this question. If we want to, we can erase this and replace it with 173.205 and 100. Right, and then I don't really have to ever worry about making a mistake in using the 200 meters per second again, right? Because it's literally gone from the question now. What is V2F? This is the red and the blue. Sorry, the green and the blue. The green and the blue is object number 2. What's the x component of that object number 2? Good, negative 173. I'm going to write that in blue here just to remind you where it comes from. And then I'm going to add to that plus M3, which is 150 times V3F. Now I'm going to do this on the calculator. Follow along with me to make sure that you can do it here. On the right side, I've got 150 times 150. I put those in brackets. Plus 100 times negative 173.205. It gives me 5179 on the right side. If they take that over to the left side, I take it over by subtracting. And then I'm going to divide by 150. And that gives me negative 34.53. So what have I just found? Not VF, but I found the x component of VF. And as I see you guys working feverishly away, copying this out, and for the most part, I think making sense to you. Like, think back a year. Where were you at this point a year ago? V equals D over T. D is 20. T is 10. What's V? Like, man, look how far you've come. Look at this. Look at this compared to where you were this time last year, right? All right, so my y component, this is still for number 4. I just ran out of space here, okay? The y component, once again, we're going to say pi is equal to pf. The initial y is still 0 because the whole thing's at rest, x and y, equals m1 v1f plus m2 v2f plus m3 v3f. By the way, if we had been given momenta here instead of velocities, we could have treated this like we did that last question, right? and avoided the mv if we wanted to. What's the final momentum y component of object number 1? The final y, object number 1. How much of that 150 meters per second is on the y-axis? None. M2 is 100. How much of that original 200 meters per second that's dead to us now is on the y-axis? Jason, how much of that original 200 is on the y-axis? 100, except we're going to make it negative because it's down. Parker? M3 is 150 times V3F. 100 times 100 is 10,000. It comes over to the other side by adding. And we're going to say 10,000 divided by 150 is 66.67. Now it's physics 20, right? Which is sometimes harder because it's been so long. But we've done this a few times now. The x component, remember, we've clearly labeled x and y here. The x component is neg 34, so draw it as neg 34. The y component is clearly 66, so draw it as 66. And then the resultant velocity is right here. V is going to be found by the Pythagorean theorem. Theta is going to be found by the inverse tan function. And when I do that, V works out to be 75. And theta works out to be 62.6 degrees. And this would be north of west because we're measuring it from the west. If you do it the other way, you could have made it, what, 27.4 degrees west of north.